Hello everyone, this is Pritam Haith. I am the Assistant Professor of Vignan Institute of Information Technology. Today I will discuss Structural Analysis 2. The discussion topic is two-hinge arch. So let us get started. First, I would like to explain what is arch and why it is required. An arch structure is defined as the curved girder having convexity in upward direction. The two main thing is it has a convexity at upward direction and it has the curved shape. This is the definition of arch structure. Now, what is the requirement to construct an arch structure? We have beam structure. As we know, the beam structure is a straight girder, but in case of arch structure it is the curved shape girder like this. We have learned the beam structure as a straight line subjected to different types of load, different types of UDL, different types of point load. So, here once the beam is subjected to different types of loads, it gets deflected. Okay? Now, the problem is that when the beams are subjected to different types of load, it gets deflected. Therefore, the bending moment is proportional to the square of the span. Once the span of the girder increases, the bending moment, the design bending moment increases. For this reason, eventually the section becomes uneconomical. But in case we can replace a beam structure with a arch structure, a beam structure with an arch structure, it will give more advantage. How? Just see, an arch structure is a curved girder. Okay. Now, when the load is applied at different position and also UDL is applied at different position, the curved girder gets compressed or the supports of the arch try to spread. Okay. After application of load, the girder gets deflected and this is the final position of the girder once the load is applied, but the girder has sufficient amount of horizontal thrust. As the girder has sufficient amount of horizontal thrust, it cannot spread, it cannot deflect, it cannot move anywhere. As the supports are fixed or hinge support, therefore, and the supports are subjected to horizontal thrust, so it cannot move from its initial position, it cannot deflect from its original shape. So, this is the advantage of an arch structure with compared to a beam structure. So, the supports must efficiently arrest the displacement in the vertical and horizontal direction. Therefore, the structure will be said that it is an arch structure, and an arch structure without horizontal thrust, it is like a beam structure. Suppose we have a arch structure, okay, we have a arch structure, but it has zero horizontal thrust, it has horizontal thrust equals to 0, then it is not a arch, it will be behave like simply supported beam. An arch structure will be said an arch structure only there will be a significant amount of horizontal thrust, then only it will be called an arch structure. In this figure you can see this is 3 hinge arch and this is 2 hinge arch. Okay. Now, in case of 3 hinge arch, it has 3 hinges, 2 hinge at supports and 1 hinge at crown. Again, in case of 2 hinge arch, it has only 2 hinge at supports only. It has no extra hinge or third hinge at the crown. Now, the advantage of arch structure is, I think it is clear. I am again explaining that for simply supported beam, the design bending moments increases with square of span, but in case of arch structure, as it is subjected to horizontal thrust, therefore, the deflection is very negligible with compared to a beam structure. Therefore, an arch structure is an economical section with compared to a beam structure. This is the advantage. That is why we use an arch structure on the rivers, on the roads for communication purpose. Now, in this figure you can see an arch structure is supported with fixed or hinge support and the girder or deck of the beam is connected with the arch with ropes. Okay. Now, as it is subjected to significant amount of horizontal thrust, so it cannot spread like this, it cannot spread as the structure, as the arch structure is supported with significant amount of horizontal thrust. Therefore, the structure cannot displaced, like this, it is intact at its original position, and then only it is said that the arch action is fully acting. Now, in case of beam supported uniformly distributed load, maximum bending moment increases with square of span. As I have explained it in the earlier slide, the beam structure is subjected to any types of load and eventually it gets deflected due to the load, and the design bending moment increases with the square of span. But in case of arch structure, as it is supported horizontal thrust, which is the most important in an arch structure, and the supports does not yield and the supports does not move from its initial position, or the deflection or the displacement of crown of the arch or supports of the arch is very negligible. Therefore, the design bending moment of arch structure is very small. Okay. This is the main advantage of an arch structure, and that is why it is constructed in different location. There are many types of arch structure. The common arch structure is 3 hinge arch and 2 hinge arch. In this today's class, I will explain 2 hinge arch. Now, by the names you can understand, once the arch has 2 hinge at its both the support, then it is called 2 hinge arch. In this figure you can see the 2 hinge arch. This is the practical example of a 2 hinge arch. It has 2 hinge at both the support, that is why it is called 2 hinge arch. Now, we are interested to know what is the horizontal thrust, as the horizontal thrust is the most important in arch structure. So, we have to determine the horizontal thrust and the bending moment generated in an arch structure at any point. So, we will derive the horizontal thrust and bending moment our intention is to determine these two parameters. Now, to know these two parameters, we need to learn the Castigliano's theorem. Using this Castigliano's theorem, we will able to evaluate the total displacement of the two hinge arch and the bending moment occurred in the girder. Now, according to Castigliano's theorem, for any beam or truss subjected to any load system, the deflection at any point r is given by partial differentiation coefficient of the total strain energy stored with respect to the force Pr acting at the point r in the direction in which the deflection is desired. The definition is long, but it is very simple. Just try to understand. It is a beam structure subjected to different types of load, may be point load, may be asymmetric load, maybe it is acting at the edge at the middle point, or maybe it is UDL. Whatever is this, due to the load system, the girder will deflect, the girder will have some deflection. Now, we will find out what is the deflection. The deflection at point r due to the load system Pr is yr. So, yr is the deflection due to the load system Pr at point r. Now, we will evaluate what is yr. Just listen that the deflection formula I wrote here, the yr is equals to del wi del p. Now, what is del wi del p? Wi is the total strain energy. Wi is the total strain energy. Now, how will you calculate the total strain energy? The total strain energy is the integration of m square ds by 2 ei plus sum of s square l by 2 ae, where m is the bending moment and s is the axial force. Here we can put the value of wi in this expression and we derive the function, we will get the deflection at point r. First we will evaluate the strain energy, then we will derivative the strain energy and we will get the deflection at point r. Again I am repeating, to evaluate the deflection at point r due to load P, we have to find out the strain energy. The strain energy equals to sum of m square ds by 2 ei plus sum of s square l by 2 ae. Ei is the flexural rigidity, m is the bending moment, s is the axial force and l is the length of the span. So, I will put the wi, that is strain energy due to the load system stored in the beam system. I will do the partial derivative of w with respect to the load Pr and I will get the deflection at point r. So, in this way we can calculate the deflection at point r. Now, let us start the derivative. We have to assume the condition to evaluate the horizontal thrust, that is the horizontal thrust at each support may be determined from the condition that horizontal displacement of either hinge with respect to the other is 0. As I have already told you, the horizontal displacement is sufficiently strong enough, the horizontal, as I have told you in earlier slide, that horizontal thrust is significant and it is susceptible to resist the horizontal and vertical movement. Therefore, the relative displacement of either support or the relative displacement of any support with respect to the other is 0. That means, the relative displacement of support A with respect to support B is 0 and vice versa. That means, the relative displacement of support B with respect to support A is 0. That means, the span of the arch structure will be constant. Okay. In no way the supports of the arch will move either inward direction or outward direction. This condition we have to apply, and then we will find out the horizontal thrust. Next, let us assume an arch structure is subjected to different types of point load, different value of point load W1, W2, W3 at different location. The span of the arch is L and the rise of the arch is H. Now, what is the rise of the arch? The rise of the arch is nothing but the distance between the crown and the furthest span. Suppose this is an arch structure, this is an arch structure. So, this is the crown for any types of arch, for any either it is 2 hinge arch or 3 hinge arch. This is the crown. From crown to the support level, this is the support level, both the supports are at same level. So, this length, this distance is called the rise of the arch, and this is called crown of the arch. Now, this is the here the supports are at same level. Once the supports are at different level, then the furthest, the distance between crown and furthest support will be the rise of the arch. So, the rise of the arch in this case, when the supports are at different level, the distance between crown and furthest support will be the rise of the arch. This is an arch structure. Let us assume that it is subjected to W1, W2, W3 point load at different level. Due to the external force, the bending moment is M. If this is an simply supported beam, just for assumption I am telling you, due to the different types of load, the bending moment at x section is M. Okay. The bending moment at x section is M. We have determined the net bending moment M minus Hy is the bending moment at any section x. Now, we will put the net bending moment here and we will find out the total strain energy on the 3 hinge arch due to the application of load on this structure. Now, if we put the value of net bending moment here and we will do the derivative, partial derivative, we will have 2 into M minus Hy into minus Hy. How this derivative is coming? It is a function like x square. So, if we do the derivative x square, we will have 2x. Okay. So, we had M minus H into y whole square. So, we wrote 2 into M minus H into y. Now, just see, we are doing the derivative with respect to H, which is the constant variable. So, which is the variable. So, with respect to H, we are derivating minus H into y. So, we will have minus Hy because we are doing the derivative with respect to H. So, y is the constant and H is the variable. So, the derivative of minus Hy is minus of y into dus by 2ei equals to 0. The relative displacement of either support with respect to the other support is 0, as the supports are either hinge support or fixed support. Therefore, no supports can move either inward or outward direction. Therefore, the relative displacement equals to 0. That means, according to Castigliano's theorem, del W del H equals to 0. Putting 0 in this expression, we have integration of my ds by ei minus h into integration of y square ds by ei equals to 0. then we can find out H equals to integration of my by ei into ds divided by integration of y square by ei into ds. If the section has constant flexural rigidity is nothing but ei. Ei is called flexural rigidity. Why? E is the Young's modulus and I is the moment of inertia, and multiplication of ei is called flexural rigidity. So, if the constant has flexural rigidity, so we can cancel this ei part. So, the net horizontal thrust equals to integration of my ds divided by integration of y square ds. This is the net horizontal thrust of 2 hinge arch subjected to any load system. Now, we will find out what is the effect of temperature when any temperature subjected to, when any arch structure is subjected to any temperature variation, then the length of the structure changes. Suppose in winter the structure is constructed and in summer the temperature rise by 15 or 20 degrees centigrade. Therefore, the length or width of the arch will change with the temperature. In the 12th standard we have already known that the change due to the temperature is L alpha t, where L is the length, initial length of the structure, T is the temperature changes or temperature variation, and alpha is the coefficient of temperature. Now, we will apply a condition. Applying this condition, we will find out the net length after application of after the variation of temperature. Now, we will apply the condition that the supports of the arch are fixed or hinge support. Okay, as the supports of the arch fixed or hinge support, they cannot move either inward or upward direction. Therefore, the relative displacement of those support is 0. On the other hand, if the support could move in outward direction, then the displacement would be delta. Again I am repeating, if the support would not be fixed or hinged, they could move in outward direction due to the rise of temperature. As the temperature is increasing, the length of the arch will increase. As it is a 2 hinge arch, therefore it has to increase the length in either support A or support B. I am assuming the support B will move outward direction. After moving the outward direction, the net displacement will be delta. Now, this delta is not possible. Why? Because a horizontal thrust is acting. Due to this horizontal thrust, the delta deflection will not be there. Therefore, due to the application of H, the inward displacement delta 1, and due to the application of temperature, the outward displacement delta will be equal. Again I am repeating, as due to temperature, again I am repeating, due to the rise of temperature, the length of the arch will increase. Suppose the length was some amount L, after the temperature rise, the displacement of the any support is delta in outward direction as the length is increasing. On the other hand, as there is a horizontal thrust, the support cannot move, therefore the horizontal thrust will try to move the arch support inward direction. Due to the horizontal thrust, the inward direction displacement is delta dash. Now, as the supports cannot move with respect to the other support, therefore delta dash and delta will be equal. That means the relative displacement of either support with respect to the other is 0. Now we will evaluate what is delta dash and what is delta. Due to the temperature rise, the delta is equals to alpha into T into L. Due to temperature rise, the delta is alpha into T into L. Now we will evaluate the displacement inward due to the application of horizontal thrust at any support. Just know the terms. B is the initial position of support, delta is B dash, that means displacement of the support, alpha is the temperature coefficient, T is the temperature in degree, and L is the length of the span. Now consider the end B as a roller with an external horizontal force H applied at B. The bending moment at any section is given by mx equals to minus hy. As we have known that this is an earth structure, at any section x, mx equals to this h into y. At any section x, the bending moment will be h into y. H is the horizontal thrust and y is the y ordinate at section x. So bending moment at any section at any section x equals to mx equals to minus h into y. Now the total strain energy stored in the arch is Wi equals to integration of h square y square ds by 2ei, because we know the bending moment equals to minus h into y. So we will put the bending moment in this expression. In the previous slide we have already explained that the total strain energy equals to integration m square dx by 2ei. So if we put the value of mx in this expression, we will have minus will be cancelled, h square y square into ds by 2ei. Now by the theorem of Castigliano, the net displacement at any support will be 0 due to the temperature, the outward displacement, and due to the horizontal thrust, the inward displacement will be equal. So delta equals to del h equals to 2h into y square ds by 2ei. Say we are derivating this function, then we will integrate. So we are derivating with respect to h. So y square is constant and h is the variable. So the derivative of x square is 2x. So derivative of h square equals to 2 into h into y square ds by 2ei. Now we have 2 cancel. So we have delta equals to h into integration of y square ds by ei. This displacement is due to the horizontal thrust hy, and delta dash equals to alpha T into L due to the application of temperature. So these delta and these delta dash will be equal. Now we will put those two delta and delta dash, equating those delta, we have h into integration of y square ds by ei equals to L alpha t. So h equals to alpha TL divided by integration of y square ds by ei. So this is the horizontal thrust when the temperature rises. So considering the temperature change, the horizontal thrust will be h equal to ei alpha TL divided by integration of y square ds. For a semicircular arch, what will be the expression, and for parabolic arch what will be the expression? Just see here. For a semicircular arch, we have to find out the value of integration y square ds, and the same expression we have to find out for parabolic arch. Now the value of y square you have to put here. Just see a small triangle here. I am drawing a small triangle here. This small triangle I have drawn here. The small triangle's altitude is ds and the base is r, as it is a semicircular semicircular to hinge arch. So the base will be r and the hypotenuse will be something, and the inclination of the hypotenuse is d theta. Okay, I am considering a small triangle at this position. The base of the small triangle is r, as it is a semicircular to hinge arch, and the altitude or the vertical distance of this triangle is ds, and the inclination of hypotenuse is d theta. Therefore, we can write ds by r equals to tan theta. We can write ds by r equals to tan theta. Height by base equals to tan theta. As the theta is very small, so we can write tan theta equals to theta. So we can write tan theta equals to, we can write tan theta equals to theta. So we have ds by r equals to d theta. Therefore ds equals to r into d theta. As we have ds by r equals to d theta, ds by r equals to d theta, so ds equals to r into d theta. So we can write here ds equals to r into d theta, and y is nothing but r sin theta, because at any section what will be the y? Say this is r, the hypotenuse is r, so this is the cos component, that means r cos theta, and this is the sine component, that means r sin theta. As this is r, so base component will be cos component and vertical component will be sine component. So this is r cos theta and this is r sin theta. So we can replace the y as r sin theta, this is y, vertical distance y. So we can write r sin theta whole square into ds. We have determined r d theta, so we put r d theta. So if we integrate this from 0 to pi by 2, because we are considering the half span and we will multiply it by 2, so we will evaluate for full span. So multiplying 2, we are integrating for half span 0 to pi by 2, we have 0 to pi by 2, we have integration of r square sin square theta r d theta equals to 2r cube pi by 2. So ultimately we have this value of this is pi r cube by 2. So we can write in this expression pi r cube by 2, and we will finally get the horizontal thrust for semicircular arch when it is subjected to temperature change, that is H equals to EI alpha T into 2R divided by pi r cube by 2, and final expression is H equals to 4 EI alpha T divided by pi r cube. This is the final expression of horizontal thrust when it is subjected to temperature change. Now we will find out the horizontal thrust when it is subjected to temperature rise for a parabolic arch. So we have to again find out the expression of y square ds. We know the expression of y square ds for a parabolic arch. We know y equals to 4h by L square x into L minus x. We know for a parabolic arch y equals to 4h by L square x into L minus x. This is for parabolic arch. Okay. So we will put the value of y 4h by L square x into L minus x whole square into dx. So if we do the integration 0 to L and multiply it by 2, this is the half span integration, and multiplying by 2 we will get the full span integration. So we will get finally 8 by 15 h square by L. So now we will put this expression into the previous expression. We will have, we get the integration we get the value of integration y square dx equals to 8 by 15 h square by h square L. So, in this expression we will put the value that we have evaluated for parabolic arch. So, we have E I naught alpha T L divided by 8 by 15 h square by L. So, ultimately we will have 15 E I alpha T L divided by 8 h square. This is the final expression of horizontal thrust for a parabolic arch when it is subjected to temperature rise. Now, we will determine the bending moment. Thus, we can determine the horizontal thrust H due to temperature rise. Therefore, now this is the final expression of horizontal thrust due to temperature rise for a parabolic arch, parabolic two hinge arch. Now, therefore, maximum bending moment due to temperature rise will be m equals to h into h, because for an arch structure, at any section x, this is the y distance and this is the horizontal thrust is acting. So, at any section mx, the bending moment mx equals to h into y. So, we will put the value of h and put the value of h. So, we have evaluated the value of capital H, we will put here, and the value of h we will put here. Say we will find out the maximum bending moment for parabolic arch and for semicircular arch. That is why we are putting here integration y square by integration y square into ds, because it will change for parabolic arch and for circular arch. Therefore, this is the common expression or this is the generalized expression for maximum bending moment due to temperature rise. Now, we will evaluate integration y square for parabolic and for circular also. Let d be the depth of the arch section. This is an arch section. So, the depth at any section you consider the depth is d. If the depth is d and the section modulus z equals to I by y, we know the section modulus z equals to I by y. I is the moment of inertia and y is the depth of neutral axis from the farthest fiber. For any beam section, you always remember, for any section, if this is the y max, this is the capital D, for any section beam or anything else, the depth of neutral axis is the axis where the no tension and no compression is there. So, y max is the generally d by 2 for any rectangular section, but it may vary. Okay. So, the depth of neutral axis from the farthest fiber will be the y max. So, for this rectangular section, we are just considering to simplify the calculation, d equals to y max equals to d by 2, but it may vary from section to section. Therefore, I by y we will put the y max equals to d by 2. So, z equals to 2I by d. Now, from the bending equation, bending stress, we know the expression m equals to Fz. From the theory of bending, we have already learned. Therefore, F equals to m by z. We have determined the m from the previous slide and we will put the value. We have evaluated the value of z, d by 2I, we have put the value. Now, finally, we have determined the bending stress due to temperature for either circular arch or parabolic arch. The expression will be E alpha T L H into capital D divided by 2 integration of y square ds. Now, for this is for circular arch. You just replace the ds as dx for parabolic arch, because in parabolic arch expression we have 4h L square x into L minus x. So, we have to integrate this function with respect to dx. Therefore, we have to replace ds with dx.